1.7 for Algebra 1. We're on page 43 in your book. The key vocabulary you'll notice is like the last one, function. Our function, our domain, and our range. Remember, a function can be represented in a table. We have x, y, okay, and like 1, 2, and 4. And that's our, the x, those are our domains. And then we could have an output of 2, 3, and 5. Trying to get these from the top of the page on page 43. 2, 3, and 5. And again, my pen won't write. I don't know if it's honestly operator error or me. I mean, that's what I meant. Operator error or software error. I'll have to look into that. There's 3 and there's 5. We can also represent a function as a rule. We can write this right here, x and y, as an ordered pair. 1, 2. This one we could write 2, 3. This one we could write 4, 5. And if you remember about ordered pairs are what we use when we have a coordinate grid. Remember the x-axis and the y-axis, and it's usually on graph paper. You know, this is all numbered out like this. The first number written is, you always start at the origin, which is right here, 0, 0. The first number tells you how many to go left or right. The second number tells you how much to go up. So 1, 2 would be right there. 2, 3 would be right there. And then 4, 5 would be up there. So today we're going to talk about representing these functions as graphs. And this is just an example, a very small example of one, which you can add in your notes. So we go to example number 1 and we graph this function. So it gives us a function, y equals 1/2 x, with the domain 0, 2, 4, 6, and 8. So I like to think right here when I see half x like this is when there's nothing between a number. A fraction is a number, and a letter, it means to multiply. So I want to use the word of in there when I think of multiplying. What's half of 0? What's half of 2? What's half of 4? So that'll help me when I'm filling out my table. So I'm going to make this table, XY table, and I'm going to make my table this way. So my domains are my x's, 0, 2, 4, 6, and 8. And then my y's, I put in the x's into the function. So what's half of 0? 1 times 0 is 0. Half of 2 is 1. 1. Half of 4 is 2. I wonder if it doesn't like my left hand. Do you think that could be it? Half of 4 is 2. And I can't write right-handed. Half of 6 is 3. Half of 8 is 4. So there's my start of my graph. Now to graph this, look what I've made here. These numbers right here are my ordered pairs. So this is 0, 0. So all I have to do is go on my coordinate grid and plot those points. 2, 1, 4, 2, 6, 3, 8, 4. And sorry, I can't write it. Let's see what they're doing here. Let's see if we can show it better. So make an input-output table, which is our table. And we got the same numbers. Plot each point for your ordered pair. So notice there's our grid. And let's see, right here is 0, 0. Right here is 2, 1. Right here is 4, 2. Right here is 6, 3. And right here is 8, 4. So those were the numbers that we just did. And so we graphed that function. Okay? So let's try this one in a guided practice. We're going to graph this function, y equals 2x. So we always start with our input-output table. Mine are going to go up and down. Just because you want to go the other way, that's fine. Well, mine might go up and down, you know, depending on whether or not I can get it made. So I get 1, 2, 3, 4, and 5. So my problem, I'm putting in y equals 2x minus 1. So I'm going to put in x, so 2 times 1, right here's where I put in the 1. 2 times 1 is 2, minus 1 is 1, and I'm very verbal. I like to say them out loud a lot. So number 2, I'm going to go 2 times 2 is 4, minus 1 is 3. And I'll show you a little trick. quick here in a second when we get up here. And I'm going to put in 3. 2 times 3 is 6. 6 minus 1 is 5. Now you'll notice, as long as these numbers are going up, these are going up by 1, these will go up by some sort of pattern. So it goes 1, 3, 5. Notice they're going up by 2. So if these continue to go up by 1, these will continue to go up by 2. So this one's going to be 7, and this one's going to be 9. And you can double check it. Let's put 4 in. 4 times 6 is 8. 8 minus 1 is 7. 5. 2 times 5 is 10. 10 minus 1 is 9. So what I've done is I've made my ordered pairs. My ordered pairs are 1, 1. Try to write them for you. 1, 1. Oh, yeah, sorry. I'll circle them. How about that? There's an ordered pair. There's an ordered pair. There's an ordered pair. There's an ordered pair. And there is an ordered pair. Let me see if they give me a graph that I can put those on. Oh, they did put them on. So you'll notice this graph, they numbered by 2. So there's 1, 1. There's 2, 3. There's 3, 5. Right here is 3, 5 right there. 4, 7, which is right here. And 5, 9, which is right there. All right? These are kind of fun, actually, as long as you substitute the numbers in correctly. So example 2, it says graph a function. So we're going through here and it says, all right, we're going to talk about SAT scores. So let's read this problem. The table shows the average score S on the mathematics sections of the Scholastic Aptitude Test, the SAT, in the United States from 1997 to 2003 as a function of the time in years since 1997. In the table, 0 corresponds to the year 1997, 1 corresponds to 1998, and so on. So 2 then would be 1999, 3 would be 2000, okay? Graph the function. So we make a table, okay? Or you'll see, right here's the table, they give us this. So 0, the average score was 511 this is in 1997, the average score was 511. In 1998, the average score was 512. In 1999, and so on, all the way up to the year 2003. So it says to graph that function. So what you have to do is now you have to decide what's my scale going to be. What are my ranges going to be? So you look at that, let me get the graph up here. Okay, you look at this. It says the years since 1997, notice they numbered those 0, 1, 2, 3, 4, 5, 6. And then this little, I kind of call it a little lightning bolt because the scores didn't start, the data didn't start until 511. So it would be a really big graph, or it would be all the numbers scrunched together. If we started with 0 and numbered by like 50s or numbered by hundreds, you'd have a whole portion of the graph from like 0 to 500 that would have nothing. So we call this a broken line graph, so we can start this line graph where we need to. So in this case, we started it at 0, and then it looks like they were going up by 510, 512, 514, 516, 518. There wasn't that big of a range in those numbers, so they could make that fit. So then the data is smaller in here, and we can kind of analyze it a little bit better. So in 1997, which is this year, the 0, the score was 511. Then in 1998, the scores were 512. I think that's 512. Yep. And then look, in 1999, the scores went back down to 511, and so forth. So there's graphing that function, and sometimes it's just picking the scale. Sometimes that can be kind of tricky. So in example 2, it says, suppose you use a scale on the s-axis from 0 to 520 in increments of 1 unit. Describe the appearance of the graph. Well, we just talked about that. If you did, so basically this is what they're saying, is here's your graph, and you're going to start right here in number 0, 1, 2, 3, and you're going to go all the way by ones until you hit 520. Just think about that. Think how big that graph would be. It would be huge, and it probably wouldn't show, you'd probably be really tough to read, and not only that, but no fun to make. Okay, example 3. write the function rule for the graph. So really they're wanting us to work backwards. Look at this, they give us the graph. Well, what did we have to do to make a graph before? We had to have a table. We had to have those values. So if you look here, what we got to do is we got to find those values. We have to find those x, y values. Okay, so we look at this, and here's our first one right here. So I went over 1 and up 2. So 1, 2. The next one over 2 and up 3. So 2, 3. The next one over 3 and up 4. 3, 4. The next one is 4, 5. I see a pattern here. So I'm going to guess 5, 6. Let's check it. We'll go over here. 5, 6, and that's all the points they gave me. So then I need to write the rule. What am I doing to x each time to get y? Y equals x plus 1. Look at that. We're adding 1 each time, which is pretty cool there. So that would be my rule. Y equals x plus 1. Let's see what they do. Make a table, which we did, and that's what they did. Find the relationship. What do you do to one to get the other? Okay, and then there was the domain and the range. Okay, write the rule for the function represented by the graph. Identify the domain and the range. So same deal. I'm going to make myself a table. I'm going to find the point. So 0, 5, 1, 4, 2, 3, 3, 2, and 4, 1. In this case, what am I doing to one to get the other? Kind of tough. It's going down, so I need to subtract something. Do you notice that? What am I subtracting? 5 at the root. 5 minus 0 is 5. 5 minus 1 is 4. 5 minus 2 is 3. 5 minus 3 is 2, and 5 minus, so I think it's y. We're taking 5 minus x to get it. And that works each time. So there's my rule. My domain are these numbers, and these are my range. So I'd identify, I would write it like this. I would go domain 0, 1, 2, 3, and 4, and I would go range 5, 4, 3, 2, 1. Alright? Alright, so let's see what happens on this one. Same deal. XY table. Let's see. These are going up by 1. So 110. 215, 320, and 425. Okay, what are these going up by each time? By 5. So if they're going up by 5 each time, let's try to take. These are hard to do, I think. I forget. Okay. If I take, they're going up by 5. There's something by 5 each time, so I can't take this times 5. If I take this x times 5, that would only be 5. I could add 5. 2 times 5 is 10. Add 5 would be 15. 3 times 5 is 20. Add 5. Or 3 times 5 is 15, add 5, that'd be 20. 4 times 5 is 20, add 5, that would be 25. So I think we got it. We're going to go 5x plus 5. And we could try, remember, I just did 5 times 1, and then I add 5. 5 times 2 is 10, add 5. So there's my rule. And it's a lot of times it's just guess and check, and it sometimes can stump you, make you think for a little while. And that's right. All right, example number 4, analyzing a graph. So we're going to look at some guitar sales. The graph shows guitar sales in millions of dollars for a chain of music stores for the period of 1999 to 2005. Identify the independent variable and the dependent variable. Describe how the sales changed over a period and how you would expect sales in 2006 to compare to sales in 2005. Okay, so let's first look. The independent variable is always the variable that's on the x-axis. Okay, so that's independent. Usually the independent variable can stand alone. It can be independent. You know, if you can live on your own and take care of yourself, you're considered to be an independent, independent person. You're independent. You don't depend on anybody for anything. So this right here, years, and basically years happen. You know what? You can't stop it. Time, just like time. You can't stop time. You can't stop the years from rolling by. So that's the independent variable. It's always the x-axis. Then this one, the y-axis, is going to be the dependent variable. And I always use this saying, does blank depend on blank? So does the sales depend on the year, or do the years depend on the sales? The years don't depend on how many sales there's going to be. The sales depend on what year it is. Some years are better than others as far as that goes in the sales. So we've identified the independent variable and the dependent variable. Describe how the sales changed over the period. You know what? The sales have gone up. The sales have been good. The trend in this case shows that the sales are increasing, and we know it's increasing because what's happening to the dots right here, if I can get my line, what's happening to the dots? They are going up. Okay, so notice it's increasing every year. So if this is, how would you expect the sales in 2006? So this is 1999, 2000, 2001, 2, 3, 4, 5. So this next one would be 2006. Since the dots are continuing to go up, I'm thinking 2006 should be greater than 2005 because everything else is going up. So I think it should continue to go up. So it's just analyzing, kind of looking at the data, seeing what it's done from one year to the next, and then deciding what I think it's going to be the next time. Let's see what they say. The independent variable is the number of years since 1999. The dependent variable is the sales. The graph shows the sales were increasing. If the trend continued, sales would be greater in 2006 than in 2005. I would agree. Based on the graph in example 4, is 1.4 million a reasonable prediction for the chain's sales for 2006? Let's see, 1.4. And let's look at this. This is 1.4 is at this line right here. Is that a reasonable number to expect? You know what? It's not really, really high compared. It looks like it's falling. These are almost going in a pretty straight line, and that would, well, I say yeah. I think it's following the trend. I think it could be a little bit higher, but I think it's very reasonable to predict that 1.4 million would be reasonable. Let's see what they say here. Okay, because it increased about 0.2 million every 2 years, and that's exactly where we're at. That's it for 1.7. We'll see you next time.